Okay, just recap what we stopped, where we stopped in our last lecture. So last lecture we stopped at Mach number. So again, Mach number equal to velocity divided by speed of sound. So need to be careful when you calculate for Mach number in the coming final exam. There's an equation to calculate the speed of sound c given by square root of RTK. Okay, the value of R is you can find in the table. T is a temperature. Remember temperature here, we will convert to Kelvin because of the constant value of R and value of K, right? Then there's another calculation for C, but for this module, we will not use this formula, okay? All right. So this is the table that you will see in a final exam. For example, table B.4, this one is for air. So if the medium or the object flying in the air, then you can use this table, table B.4 in the air. So you have a temperature and all the parameter in this table. For example, the K and the C value you can straight away use from here, or sometimes you need to calculate using this square root of RTK. Okay. All right. And we're going to look at how we apply this formula in this tutorial question. Okay, so let's look at your screen. Your screen is having a picture, which is an aircraft that flying at a velocity of v. So the statement gives you the aircraft cruise means it's flying horizontally at 250 meter per second at altitude of 10 kilometer. Okay, 10 kilometer above sea level. So and then you're given a table to refer to. So by looking at the first statement on your screen, you know that you're given the velocity and also the altitude or the height of that aircraft. So this table, you're having an altitude. Okay, so you look at altitude 10,000 meter because this is a 10 kilometer. This table is in meter, so you go look at 10,000 meter, and you're going to use the value along this row. Okay. So what is a task that we need to solve in this tutorial question? First, we calculate the Mach number and also the stagnation pressure and temperature in this case. The second task is to compute the Mach number and also stagnation pressure and temperature if the aircraft increase the speed to 500 meter per second. Means it double the speed. What happened to the Mach number? What happened to the pressure? What happened to the temperature? Then task number 3 is to compute the same quantities, meaning you compute the Mach number, stagnation pressure, and temperature, but now the altitude changed to 1 kilometer above sea level. So for task number 3 or C, you need to refer to 1 kilometer, which is 1,000 altitude, this one, and this row, and use it to substitute value inside the formula. Okay, so this basically, when it comes to application kind of problems, it will tell you that there's an aircraft cruising at certain height. For example, in this case, 10 kilometer at V1. Then after that, it accelerates to V2 at this point, 10 kilometer. And then after that, it reduce for approach and landing. So when it comes to V3, and the altitude is 1 kilometer. So basically the question it asks you the application of what we learned, the Mach number, the pressure and temperature at these 3 locations. Okay. So let's look at how we solve for the first task. So first task, again, you are given the altitude of 10 kilometer, velocity 25. So you need to find the Mach number, stagnation pressure, and temperature. So first thing we look at is from table C.2. You see on your screen here. So you go and look at pressure and temperature. Pressure and temperature at 10 kilometer. So from this table, maybe the number is a bit small on your screen if you're using handphone, but if you're using computer, I think you can see clearly along 10,000 meter, 10,000 meter, all right, or 10 kilometer, you can see that the pressure is 26.5. Okay. It's over here. So temperature is this column, pressure in this column. So you're looking at temperature is this one. However, this one is in Celsius. Okay, so Celsius is minus 49.9. You need to convert to Kelvin. So you need to plus what? Plus 273.15. Okay, around that, around this value. So you get Kelvin, and also the pressure here is 2.65 E plus 4. E plus 4 means 10 power 4. So 10 power 4 is 2650 Pascal. Okay, so it's 2650 Pascal. Okay, in this table, you're seeing Newton over meter square is equivalent to Pascal, and you need to know how to convert E plus 4 equal to what? Okay, E plus 4 is 10 power 4. So sorry, 10 power 4 is 26500. Okay, it's not the answer I give you just now, because 2.650 when you multiply by 10 power 4, you will get 26500. Okay, you can write either in kilopascal form or in a normal Pascal form. Okay, so if you write in kilo, then you get 26.5 kilopascal. All right. Cool, you understand how you get pressure and temperature in this case? Who are you there?
Yeah.
Do you understand how to get pressure and temperature?
From the table.
Yes, correct. You understand, right?
Yeah.
Okay, good. Anyone you don't understand how to get 26.5 and temperature equal to 223.3 Kelvin? Because later in section C, I'm going to ask question. All right, so you understand?
Sir, I
Yes.
don't know about the temperature, sir.
Temperature?
I can't understand how the P. Okay, the pressure I get it. The temperature I
Okay.
don't know.
Yeah,
How to?
temperature from this table, what is the unit of temperature?
Oh, sir. Okay, I get it, sir. So we need to
Ah.
add 273, is it?
Yes.
Okay.
Because we are using Kelvin.
Yeah.
Why Kelvin? Because the Mach number just now, the definition of Mach number, the R value is in Kelvin. So you need to change Celsius to Kelvin.
Okay, sir. I get it. Thank
All
you,
right.
sir.
Okay. All right. So next, you at the same time, just save your time since you're using table. You go ahead and find 1 kilometer pressure and temperature, which is at this row. Okay. 1000 temperature is 8.5 Celsius. Again, change Celsius to Kelvin. And then go ahead and find pressure. Pressure is 8.988 E plus 4, which is 10 power 4. Then you'll get 89880 Pascal, or you can write in kilopascal, right? So these two numbers give you this one. Okay, then the rest is just mathematics substitution. Recall equation for Mach number, velocity divided by local speed of sound. Call out local speed of sound equation, C equal to, or you can use A to replace C here. So speed of sound equal to square root of RTK. Substitute the value of RTK, 299.6. Again, where you find RTK, let me show you the table that you should refer to, which is this one. Okay, table 1.8 is also very famous. Table 1.8, you look at the air, and then you use this R, you use this K, temperature you find just now, right? So you use the R in this table, K in this table, temperature used in Kelvin, because you see the R gas constant here, joule over kilogram dot Kelvin. So you need to change the T into Kelvin. All right. So back to the question over here. So I did explain how to get RTK, but the table I do not show on this screen, but it's from the table 1.8. You substitute, you get C 299.6 meter per second. And during final exam, if can, give the answer in 3 decimal place. Okay, if can. All right. So you substitute value, velocity is given, velocity is 250 meter per second, divided by 299.6, you get 0.8. Okay, you get 0.8 Mach number. 0.8 Mach number is a dimensionless because you cancel meter per second above and meter per second below. You cancel the 2 unit. There is a Mach number is a dimensionless, do not have a dimension. It's just a ratio that tell you what is the Mach number. Okay, and again, one important concept for compressible scenario is that when your Mach number is more than 0.3, then you're having a compressible dimension. Then equation for isentropic, for non-isentropic, it will come into place. Okay, so you have a compressibility effect on the object. Okay, that's why your assignment number 1, we are looking at the compressibility effect. Right? That's why in your simulation, in your assignment 1, you're seeing a shock wave, you're seeing some phenomena above the wing. Okay. All right. So again, you get 0.8. What mean by subsonic speed? Subsonic speed means the Mach number is less than 1. Okay, this is just an add-on information. If Mach number less than 1, we call it subsonic. SUBSONIC. If Mach number equal to 1, you're having a sonic speed. However, Mach number only happen very fast. It's either less than 1 or more than 1. Mach number equal to 1, you will see a shock wave happen. So later, we will learn the phenomena, what happens if you have a sonic case. Then if your Mach number more than 1, you have a supersonic scenario or supersonic speed. Supersonic. Okay. Right. So these are the names that important when you communicate with aircraft designer or fighter jets designer or anything that go beyond Mach number 1. Okay. Subsonic, sonic, and supersonic. All right. Next, we will go to determine the stagnation pressure and temperature. So since we have a Mach number of 0.834, so table D1. So let me see. If you go to your Moodle, you move down. There's an appendix. Let me see. I include appendix D in your. Okay, don't have. Okay, later I'll give you this one. Okay, so if you refer to an appendix table DI, so table DI is having a table with isentropic flow function. So inside this table, there are lots of numbers there. I just crop a small corner for references. Okay, so this number, Mach number that you calculate previously is 0.8 something. So 0.8 something is within here. Okay, within 0.8 and 0.5. So you need to do interpolation to get T over T0 pressure, density, area. Okay. So again, this table is for K 1.4. Okay, table 1.4. Okay. So you do interpolation. When you do interpolation, at the Mach number 0.834, you will get 0.633. So it is about here. Okay. You do interpolation between these two numbers. Use the number 0.834. Okay. You find this number. Okay. So if you forget how to do interpolation, I think you need to call Engineer Ma, teach you how to do interpolation, or maybe your previous secondary school at Max teacher. Okay, so you do the same for temperature. You get the one number. After you do interpolation between these two numbers, 0.88 and 0.87, you get about 0.878. Okay. Because the question only asks you to calculate pressure and temperature, so you only look at temperature and pressure. In later section, you will see density and also area. So table D1 or DI is important when you look at isentropic flow, or you have a you have a compressibility scenario. Again, compressibility happen when your Mach number more than 0.3. Then what happened to the stagnation pressure? There is an equation to calculate. So to find the stagnation properties, we will use pressure at 10 kilometer divided by stagnation pressure P0. Okay, same with the temperature. Okay, same with the temperature. Apologize for my typing. Let me see if I'm able to show you my full screen. Okay, you substitute, you get P0 of stagnation pressure equal to 41.86 kilopascal, and temperature at stagnation pressure, stagnation temperature also you can find from this equation. Okay, there's a typo error over here. It's not P, but it's a T. So you have 200 something Kelvin. Okay. What else? Okay, so basically you have this number. You have this number on the left hand side. So if you use at 10 kilometer altitude, you just substitute over here. You have the pressure at 10 kilometer. Right, how to get this number? If you refer to the previous slides, you have the pressure from table C.2. You have a pressure at 10 kilometer, temperature at 10 kilometer. So you substitute in using this ratio equation. Okay, so you manage to find the stagnation pressure equal to 41 kilopascal. You do the same for temperature, you get 200 something. Okay, what happens if you increase the speed? You repeat the same formula, only substitute the speed for velocity. You change from 250 to 500 over here. Because you're using the same medium, be careful on the temperature because, temperature still same because you're still at 100. You're still at 10 kilometer altitude. So temperature still same, Kelvin still, K still same. So you still get the same C value, 299.6. So you substitute, you'll get your Mach number is 1.7 or 1.669 when you increase the speed to 500 meter per second. So your Mach number is more than 1. So in this scenario, it's under supersonic flow. Supersonic flow, more than 1. All right, so there's a statement here. And also to find the temperature and pressure, again, use table D1 or DI. So you are having a Mach number of 1.669, which is within here. So you need to do interpolation between the numbers. Okay, between the set of number above and below, you manage to find the temperature ratio at this Mach number, pressure ratio at this Mach number, and then substitute the pressure accordingly. So if we do interpolation from this table, your P over P0 at 10 kilometer at Mach number 1.669, your value will be, this value will be 0.212 will be here. Okay, you do the same for temperature later on, you get the 1.63 something or 1.64 something. Then you substitute the value inside there. Okay, you will get your stagnation pressure equal to 125 kilopascal and temperature at stagnation 0. Sub-0 means stagnation, meaning at that particular point that doesn't move. So T0 equal to 347.8 Kelvin. Okay, so this basically for your task number 2 to solve the velocity at 500 meter per second at 10 kilometer altitude. Okay, let's see what happens if you reduce the speed back to 250 meter per second. However, now at 1 kilometer above sea level. So you already found the pressure and temperature at 1 kilometer from the table just now. Just recall the formula for Mach number. Mach number equal to velocity divided by local speed of sound. So local speed of sound give you by square root of RTK. Now the R will be changed because the temperature at 1 kilometer will be different from the previous one. K value will be different. T value will be different. R value will be different. So you substitute the value. You get C equal to 336.5. You substitute the V velocity 250 divided by 336, you get 0.7 something. Okay. So you repeat the similar process. You get stagnation pressure equal to 129. Temperature stagnation equal to 312 Kelvin. So this is how you solve it for task number 3. Okay. Next, we look at compressible flow regime. So you look at your screen, you're having a chart here. So chart is important to study the axis. So on the left-hand side, the y-axis is CD. The below there, your x-axis or horizontal axis is Reynolds number. Okay. Okay, so Reynolds number is important parameter for this module. So you need to know how to calculate Reynolds number. So as you can see, what happened to the Mach number? All these 0.3, 0.5, 0.6, 0.7, 0.8, 0.9, and 1 will be the Mach number. Okay, will be the Mach number. Okay, can you, from this graph, can you elaborate what happened to the CD if you increase or you reduce the speed? Okay, what happened if you increase or decrease the speed? What happened to the CD value? Okay, I'll just give you a hint. Let's say I pick Reynolds number 5. This one. What happened if you increase the Mach number? Okay, what happened if you increase the Mach number? What happened to CD value? Observe the graph. I'm going to ask question. My question is, when you increase the Mach number from 0.5, 0.6, 0.7, 0.9, and 1, what happened to the CD? The CD value is increasing or reducing. So I will just refer to one Reynolds number and then tell me what happened to CD. Yeah? Okay, let's check. Dinesh, are you there?
Yes, sir.
Okay, Dinesh, what happened to the CD if you increase the Mach number? The CD is increasing or decreasing?
Decreasing.
CD decreasing.
Yeah.
This is Dinesh's answer. Dinesh, why your answer is decreasing? Can you tell me why?
Because the lines are getting down. The curves.
Okay. At Reynolds number 5, 10 power 5, which is the red line that I draw. Dinesh, tell me the roughly value when the Mach number is 0.5. What is the CD value you read from this graph? What is the value? If the Mach number is 0.5, what is the CD value if you read from this graph? And I focus on Reynolds number 5, 10 power 5, which according to the line that I draw. What is the value of CD from this graph? Dinesh?
Yes, sir.
Yeah, what is the answer? Can you identify which line is 0.5 or not?
I think the upper one.
What does Mach number 0.5 mean to you? This line, right?
This line.
This line, right?
Yeah.
So where is your Reynolds number intersection? 0.5.
It's on 0.375.
Okay. 0.38 lah. Okay, now tell me. Your Mach number increasing to 0.6. What is the value of CD?
Zero 0.6, sir.
Where is the 0.6 line again?
In 4.8, 0.4.8.
Okay, now you increase the Mach number to 0.7. What is the CD value, Dinesh?
It is 0.58.
So back to my question, Dinesh. When you increase your Mach number, what happened to your CD?
The CD is increasing.
So why do you answer in decreasing just now? Do you understand now?
Yeah.
Okay. Cool, do you understand?
Yeah.
Understand, huh? Okay. Okay, good. Shirley and Raj, I did not ask you guys because I assume you guys understand. Huh? Stop me if you're not able to understand what I asking your friend. Okay, so as you can see, when you have a compressibility effect, why we start with a 0.3? Because if your Mach number more than 0.3, only compressibility effect take into place. Huh? So this graph we start with 0.3 and no other value less than 0.3. Okay, so this is a very simple question. Huh? When you look at graph that deal with CD, Reynolds number, so in textbook or in handbook that deal with compressibility, normally you won't find value less than 0.3. Okay, unless there's a specific research in that particular speed, then you will see line come out from there. Okay, so just take note on this one. Next, we're going to start with a pressure wave, a pressure wave. So let's say, okay, recall the Mach number equation. Mach number equal to velocity over speed of sound. What is speed of sound? Is square root of R T K. So it's in the unit of meter per second. Okay. So if you look at this diagram, how to read this diagram? So let's say you have a source of ping, or you generate a signal at t equals 0. You start generating the signal at this source. So after 1 second, t equal to 1 second, your wave will move a distance of c from the source. So you get a circle with the radius of c. Okay, so let's say your your speed of sound, let's say I give a number. Let's say your speed of sound is 100 meter per second. So after 1 second, the wave will move 100 meter from the source. So that's why you see a circle with label as C from the circle. Raj, you able to understand? If your C is 100 meter per second, your radius from the source is 100 meter. Can you see this one? Raj, you able to understand? Raj, are you there? Raj, are you there?
Yes, sir. Yes, sir.
Okay. Do you understand how to draw the solid line of C after 1 second?
Not so, sir.
Where are you just now?
No, I'm here, sir. But I didn't understand not very well, sir.
Do you understand what is speed of sound? Let's say I
Yeah.
just write 100 meter per second. Do you understand what mean by 100 meter per second?
Yeah, it's speed, right, sir? Meter per second.
Okay, so after 1 second, the wave move how long? What is the distance covered by the move by the wave?
100 meters per second means.
Okay, so let's say you have a source, you generating a sound. So after 1 second, where is the wave move? How long the distance move from the source?
So 100 meters for per second.
100 meter. So we label as C.
Okay, so that's why they got give 2C, 3C. Is it, sir?
Yes.
Okay, sir.
If 2C means 2 seconds.
Yeah.
3C means 3 seconds. Anyone, you don't know how to draw this diagram? Let me know now. We're being asked to draw the pressure wave in 4 seconds, 5 seconds. Do you know how to draw? Let me know. If you don't understand how to draw this one, let me know now. Okay, I assume everyone know. Next, I'm going to give you a more complex scenario. Okay. So all of you understand when your pressure, when your velocity equal to 0, meaning the star and the source do not move, meaning you just stand there, you just stand at the center, and then you start ping, you start generating wave. So after 1 second, your wave reach here, 2 seconds, you reach here, 3 seconds, you reach here. That's why the label of this chart or this photo is t equal to 3 seconds. So 1 second, 2 seconds, 3 seconds. At the velocity equals 0, meaning the person or the source doesn't move. Okay, I assume you understand this one. Next, I'm going to show you something new. Okay. So some new notation is that if you see T wave means the time denoted by the wave. So T wave, for example, T wave at here, T wave at the first circle equal to 1 second. T wave at the second circle is 2 seconds. T wave at the third circle is 3 seconds. Okay, now I will show you the second. Okay, how to find the radius. You take the differences of time times the speed of sound. You get the radius. Okay. So this is a simple formula to calculate the R. Next, we have a moving point already. We have a moving point. As you can see from the diagram here, we will show you the phenomena at 3 seconds. However, the velocity is less than speed of sound. Velocity is less than speed of sound. Okay. So how to draw this diagram? Okay. First, you stand at a position. You stand at one place. Okay. T equals 0. Next is that so after 1 second, your position will be here. T equal 1 second. However, the velocity is less than speed of sound. So you can see here from this table, you are generating the sound. Okay, let me start with here. It's 1, 2, 3. Okay. So as you can see the wave that you draw. Okay, let me think how do I explain to you. Okay, let me draw the 4 location first. T equal to 2 seconds. T equal to 3 seconds. Okay. The distance between the point that you see on the graph is the same distance. Okay, why same distance? It's because the velocity that you move is the same. Okay, the v that you move is the same. However, the speed of sound that generated by that location is a bit different. So for example, this one, maybe I explain in so this is the effect after 3 seconds, after what you see in the 3 seconds. So at t equals 0 here, when you pink, you will get the big circle outside. Right here. 3 seconds. After 3 seconds, the wave will reach the outermost distance after 3 seconds. Okay. Let's say your speed of sound again. Your speed of sound is 100 meter per second. So after 3 seconds, okay, your speed of sound is 100 meter per second, and let's say your velocity less than you're running, not running, but you're moving less than 100 meter per second. Let's say I just use half of the speed. If you are running 50 meter per second, which is not possible, right? Let's say you sit on the devices that can move at 50 meter per second. So after 3 seconds, the outer is the sound that travel. Let's say the origin that you transmit. After 3 seconds, the outer layer will move 300 meter, correct? Correct. After 3 seconds, this one will reach 300 meter. Let's say your speed of sound is 100 meter per second. Correct. And then when you move at 50 meter per second, so the second, I mean the after from the origin, what is the distance you move? Is 50 meter, right? After 1 second, you move to the left. You move 50 meter. then you generate the second wave again. Okay, you generate the second wave. I change to different color. Maybe like this. So at this location to this location is 2 seconds already. If you look back the history, so because we stop our action stop at 2 seconds. So after 2 seconds, the blue color distance from this position will be 200 meters. Okay, then at the next second here will be, let's see, I change to, so here to here, you move another 50 meters. All right, so from here, you generate another sound again. So this sound is another 1 second. Okay, so this 1 second is 100 meters. So as you can see from this diagram, when you are moving less than your speed of sound, you'll get 3 circles that you can see that the centroid of the movement is towards left hand side. Is toward left hand side. Yeah. So it will take some time to process this diagram, but if you understand what I'm drawing on the right hand side, you're able to link to this diagram. Yeah. So it will take some time to digest this diagram. Okay. So you will see that the wave is squeezing each other at the left hand side of the diagram here. Okay. Right. So this one, it will take some time to digest. So what happens if you're moving at the speed of sound? The diagram at below. All right. When you move at the same speed of sound, again, I draw the diagram again. Let's say you running at the same speed at the speed of sound. 3 seconds. Okay. So maybe I'll just take this one as T0, T1, T2, 2 seconds, and so on. And this one, T equal to 3 seconds. Let's say I use 3 seconds to move, meaning the yellow is you are running to the left. Okay, you're running to the left and complete the race in 3 seconds. Your velocity of running on the vehicle, your V velocity is, let's say, 100 meters per second. Let's say, and the speed of sound at that particular location, the speed of sound is 100 meters per second. Meaning you are meeting the speed of sound. So what is the distance you travel in the first second? You travel at 100 meters per second. You travel at 100 meters. So, and then another 100 meters. And then another 100 meters. So let's draw the wave that generate after 3 seconds. So I'm going to draw using a different color now. So after 3 seconds, what will the distance travel by the origin wave that you generate? After 3 seconds. After 3 seconds, you are the wave will reach 300 meter. Okay. Then after 2 seconds, if you draw another circle, after 2 seconds, let me change the color to blue. So after another second, let's say 2 seconds, after 2 seconds, so you're going to reach 200 meter. And then after another second, here, because the distance is 1 second. So here you're going to move 1 second. So you're having another circle, but the line is touching each other. Here is 100. So you're going to get the diagram that you see over here at the center. So you see the wave is squeezing at the one tangent point. Okay, this one you can use graph paper to plot the circle. So if you're moving at the same speed as the speed of sound, with its velocity equal to speed of sound, you're going to get an intersection point at one of the distance from the origin. And you can plot a tangent plane. We call it Mach wave in this one. So a very interesting phenomena is that if you're standing on the left-hand side of this tangent plane, you will not hear any sound. You will not hear any sound generated previously. We call it zone of silence. However, if you're standing at zone of action, if you stand here, you will hear sound after 3 seconds. After 3 seconds, the sound is made at this location. Okay, so there are two zones there when you're having a speed of sound equal to your velocity. You'll get a zone of silence and zone of action with the tangent plane. Okay, so have a careful look on the diagram. Make sure you understand what happens if you increase your velocity. Okay, you're having a Mach wave with its tangent to one point from the circle. On the left hand side or in front of the Mach wave, you won't hear anything. But behind the zone action, you will hear a voice. For example, let's say you have an aircraft, a fighter jet, flying above you. And this fighter jet is making this Mach wave. So you are hearing some voice from the aircraft. However, if your friend stand in front of the jet, he won't hear the jet is coming. Only can hear the jet after this Mach plane. This scenario only happen when the velocity equal to speed of sound. Okay. Meaning this fighter jet is moving at speed of sound. Velocity of this fighter jet will equal to speed of sound. It will form one tangent plane in front of the aircraft. So if you're standing in front of the zone of silence, you won't hear anything. But if you are at behind the aircraft, then you will hear the jet after a certain time from the distance. Okay. Next, another interesting phenomena, when you are moving faster than the speed of sound. Okay, when you're moving faster than speed of sound, you will meet a phenomena called you're having a Mach cone happen. Okay, you're having a Mach cone happen. What I mean by Mach cone? This area outside the cone will have a zone of silence, meaning even you stand in front or even you stand at this zone, you won't hear the sound until it reach you. Okay, so if you are in this outside the cone, you won't hear any sound. So we name this zone of silence. Okay. So you will take some practice to understand this diagram. Okay, you can use a graph to plot this phenomena. Let's say you fix your Mach number equal to 100 for the third diagram, and you have a fighter jet or you have a vehicle that move maybe 150. Then on the graph itself, you can plot after 3 seconds what happened. Okay, so you have 4 points here. So meaning after 3 seconds, you have 1 circle. After 2 seconds, you have 1 circle. After 1 second, you have 1 circle, and you join the tangent of the circle. You will meet at 1 point. You call it zone of silence or Mach cone. The cone that you see here is a Mach cone. And inside this Mach cone, you hear a loud sound. Okay, so these 3 graphs explain why military they are interested to invest money in the supersonic fighter jets, because you can reach your target before your enemy detect your movement. Okay, as you can see, the sound is, if you can fly faster than speed of sound, your enemy will not detect you. Let's say your enemy is at the side of your aircraft. Your enemy might not detect you if you fly faster than the speed of sound. So you will form a phenomenon called Mach cone, that if the enemy is within this Mach cone, then only you are detected. But outside this Mach cone, you are not able to detect. Okay, so this is the application of a compressible flow chapter. Okay. Okay. So I'm showing you these 3 diagrams. So spend time to understand these 3 diagrams and with some side note there. So on the left hand side, if you are less than speed of sound, then we call it less than Mach number 1. If the ratio V divided by C or the Mach number less than 1, you call it subsonic. If the ratio or the Mach number is 1, we call it sonic speed. If the Mach number is 1, more than 1, we call it supersonic. Okay, so under supersonic, Mach cone is happening. Again, what is the alpha angle that you found in the Mach cone there? There's an alpha angle there. So you can calculate the alpha angle by using sine alpha equal to C speed of sound divided by B, or is the inverted of your Mach number. Okay, so this formula is important when you are studying supersonic flow, when you're interested to find where is the zone of silence, where is the zone of action from your source. Okay, right. Okay, so this one you can read. So important, when your Mach number less than 0.3, you're having incompressible flow. When you within 0.3 and 1, you get a compressible because your Mach number is more than 0.3. More than 0.3, it become compressible. However, if less than 1, call it subsonic. And if your Mach number more than 1, it becomes compressible. Again, why compressible? Because your Mach number more than 0.3. And those Mach number more than 1, we call it supersonic flow. Okay. And so on. There are some other textbook or technical word, transonic and hypersonic, that you can read from these slides. Okay, after we go for a short break, then we will discuss this tutorial question. Okay, let me stop the recording.